Everyone, today's Wednesday, April 9th, 2025. Today we have Jim. I'm announcing that probably we're going to end this class in a couple weeks just because it's taking too much time and I don't have people coming in to pay the bills for the platform. So I'm going to propose that we meet just informally once a week, like on the first Wednesday of every month, and just meet on Zoom and have fun. Um, but we'll talk more about that because we have two more speakers over the next 2 weeks. But keep an eye on the platform for an announcement. And I will turn it over to Jim Steele in California.
All right. I just lost the screen that was going to allow me to share my screen.
Yeah,
Uh, where the heck is all that? I had too many things open too. Um, I apologize for all this. Where are you? The Zoom.
I don't know. I don't bloody
Oh,
know.
there I am. Okay. Now I see everybody now. Different screens come up. And I want to share my screen. I think that's the one I want.
got it.
So are you all seeing three? Let me see, I have to start two. Okay, so I got like three panels there. Does everybody see that? Good. All right, so if you haven't heard me talk before, I'm an ecologist. Uh, I did 30 years of research in California, Sierra Nevada, and wildfire was one of the things I looked at, as well as climate. To be a good ecologist and understand how ecosystems work, you have to understand climate change, El Nino, La Nina, fires, to see how the ecosystems are all responding. So I've published many posts on different ways, YouTube and Twitter, kind of railing against some of these climate scientists that are blaming a wildfire crisis on global warming. And I want to kind of go through the reasons against that, why I think there's no data to really support it. It's just a theoretical assumption, and kind of give you an overview of why we have the certain amount of fires in different places due to the way the climate is working. So if we first look at just some of the data that I know from the Oregon wildfire history, shows no correlation with rising CO2 or warmer temperatures. Many more fires in Oregon happened in the 30s and earlier. Likewise, there had been studies in the Southwest of the United States that showed the 1700s and 1800s had far more fires. And then around the 1900s, wildfires started to decline in that area. And that was due to policies of fire suppression. People were afraid that these wildfires were taking out valuable timber. So by the 30s, the National Forest Service implemented what they called the 10 a.m. rule, meaning if they spotted a wildfire, they would muster all their resources to have it put out by 10 a.m. the next day. And that began the era of suppression. But we look back then, there were far more wildfires during, it was cold temperatures, it was low CO2, it was a little ice age. Then around the 80s, there's been a slight uptick in fires, nothing even approaching what it had been for 2 centuries. And the reason for that was mostly because we realized that by doing fire suppression, we were allowing understory growth to build up. And that was gave the ability for a small fire now to kind of decimate the forest more than it ever had. Now, if you want to convince people that it's climate change, you cherry pick just everything since the 1980s. And so our EPA shows this graph and showing since 1980, there's a tremendous uptick, but it totally ignores historical evidence. So that was the first thing that annoyed me, among many different things. So I want to start looking at what are the things that cause fire. And number one is ignitions, but we've had studies from several researchers saying that a rise in global temperature will increase lightning strikes, and that could cause 12% more fires. And you have higher temperatures that boost convection, et cetera, et cetera. And, just to start off with, I don't know, in Great Britain, if you had Boy Scouts like I did, but you always learn the fire triangle, that you have ignitions, the wind, and the fuels. And it doesn't matter how dry the fuels are, for how long they've been dry, they don't start a fire unless there's ignitions. So how much are ignitions normal? Well, if we look at the data for the United States, you see that natural lightning season kind of peaks through June through August. And it's hardly any fires from natural causes between January and April. But what that red area shows you is human ignitions have caused a tremendous expansion of fires throughout the year. And alarmists like Michael Mann have said, oh, global warming is causing fires to happen all year round. But it doesn't happen to do with warmth. It has to do with humans. And the closer correlation is that as you increase human populations, you get more accidental fires, more careless fires, more arson. You have an electrical grid that's more susceptible to high winds. And you have more easily ignited landscapes and going along with the natural dryness. So it's this human population that they don't like to push. They try to keep the focus on CO2 and fossil fuels in a climate crisis because that gives the government the reason they should regulate whatever you do.
Jim, can you go back one sec?
Okay.
I'm just speculating there's a spike for July 4th because of the United States, but it looks like mid-June. Do you know about that?
It's offset. It's July 4th. It's
It is
fireworks.
July 4th.
It is July 4th. And
yeah. So this is US data.
This data is for the contiguous United States.
Right.
The 48 states. So
right. Okay, that's 4th of July celebrations with fireworks, just so everybody knows.
We freed ourselves from the tyranny of the Brits, and I don't know if I'm offending anybody with that, but anyways.
Yes. You should still be paying taxes.
Tea Party, all that. If you look at the causes of fires around the world, United States, 85% of the fires are human caused. In California, 95% on Forest Service land is human caused. And in Southern California, where we just had the big Los Angeles fire, 100% is human caused. They don't have lightning strikes there. And I can always tell when it's a lightning strike because they usually tell you that right away. They can see that on their weather radar. Well, when they hold up saying, well, we're still investigating what caused it, is because they're trying to figure, was it arson? Was it an electrical fire? Was it irresponsibility? If you look at Australia, they estimate 85 to 90% of the bushfires are all human started, and they estimate 50% by arson. You go to Greece, where they've had some big fires, and everybody thought that meant the world was on fire. 90% of the wildfires are attributed to humans, with, again, a high percentage of arson. Portugal is probably the most, that and Spain are the more fire-prone areas in Europe. Again, 95% of the wildfires they attribute to human ignitions. And you go to Brazil, 95% of their wildfires are human-induced, and a lot of it's people deliberately trying to clear the forest for agriculture or ranching, and then those fires get out of hand. So you see this data and say, oh, the world's getting more wildfires, where human ignitions are what it is, but it doesn't fit the narrative of a climate crisis. So often that point gets played down. So how much does lightning really cost? Well, if we look again at the United States, where do you get the most lightning strikes? And Florida is the clear winner. And then you see the areas are red. So it's the eastern United States gets the most. The western United States gets hardly any lightning strikes. So how does that correlate with the number of wildfires in the United States? Well, and this is the wildfire potential. The eastern United States has the lowest potential. The western United States has the highest, despite the lightning strikes. And that has to do, and I show it from here, is relative humidity is what really controls the ability for these fires to be ignited and spread. And you see, it's the western United States it has a lowest average of 20 to 40% relative humidity. In the fires we had in Los Angeles, the relative humidity got below 10%. Where in the eastern United States, relative humidity gets up to 70%, even higher. And actually warmer temperatures increase the circulation of moisture out of the Gulf of Mexico into the eastern United States. And so in this case, eastern United States suffers some of the least amount of fires because warm temperatures increases the circulation and brings more moisture to it. If we average, say, over the last 40 years, the West has burned 170 million acres compared to the eastern United States, 50 million acres. So it's completely contrary to what you want to think with natural ignitions from lightning. So why is California so bad? And actually Southern Europe, the Mediterranean basin, they're Mediterranean climates. And Mediterranean climates are defined as having hot, dry summers. In California, we get no rain from June through October. And it's probably very similar, even though the Mediterranean Ocean will cause a little difference on that. But then you get mild, wet winters. And the reason for that, at that latitude between 30 and 45 degrees north or south, the trade winds are blowing from the west to the east. And you would think those winds would carry a lot of moisture across the ocean and bring it to California and keep us wetter. But what happens is when the sun moves north due to the tilt in the axis, the direct rays go further north. There's a high pressure system that also moves there, and that blocks the rains from reaching California. It blocks the rains from reaching the Mediterranean, and there's a very symmetrical response in the southern hemisphere that mirrors this for the winters. But what that does is it sends all the moisture further north. So moisture that might go to Spain and Italy and Greece goes up to Ireland and Great Britain. So you get the Emerald Isle that gets plenty of rain. In the winter, that high pressure system now shifts to the south. And that kind of opens up the gate so we can get most of our moisture in the winter. Well, if we look at California's largest fires, even though I said lightning is really not the issue, our biggest fire was the August Complex fire. But all the others, the Dixie Fire, which was near me, the Mendocino Complex was near me, Park Fire, I know all these intimately. They were all started by humans, electrical sparks from a stake or arson. The reason the August Complex fire happened is because California is so dry during the summer. If you can see in this, there's a plume of clouds coming off of the Pacific, which is unusual. But that brought a layer of very moist air above a layer of very dry surface air. And when it rained, the convection there caused it to rain, but the rain doesn't reach the surface. So we call it virga. I know I would imagine people on the East Coast never heard of virga because it means that the rain falls from high in the sky and never reaches the surface. And sometimes it can be very beautiful. I was walking out in the morning with a virga. It was like a veil that was all lit up orange and red from the morning sun, but it stayed maybe a couple 100 meters above us. But we're walking like through this veil of virga, which was pretty impressive. But when you have dry lightning, there's no way that usually when lightning happens, it happens with a rainstorm that minimizes ignition and minimizes a fire. But when you have virga, like this happened, this dry lightning caused one of the biggest fires in August when California is at its driest and over an area that's mostly filled with very susceptible types of fuels like grasses and shrubs. And if you compare these fires, the biggest one, Los Angeles, I imagine everybody heard about Los Angeles being on fire, that area in the Pacific Palisades. It was several fires where it definitely wasn't lightning. There's been some arrested, and they think was due to arson, but there was only a total of 57,000 acres. And you compare that to these other fires that we had, or 500,000 to 1 million acres. It gets a lot of press, but you really don't understand. And the Los Angeles fires didn't happen when it was hot. It happened end of December, early January, when it was the coldest. And if I just kind of look over at Europe, you can see most of the fires are in the Mediterranean basin. Spain and Portugal get the most fires. In southern Italy and Greece, these are the places have the highest fires naturally because of this Mediterranean climate, that it's dry most of the summer. Where up in Ireland and England, you guys hardly get any kind of fires up there. So you have to look at different places and look at how the general climate is working to why we see fires in certain places. Now, the second part of that fire triangle is the winds. And the winds do two things. They can dry the vegetation, and they can dry it very quickly, and they more rapidly spread the fire. So if you're looking at burnt area, how much has this fire been caused? It's not temperature that's going to make it burn much more. It's going to be how the winds dry it and spread it. So if you look at relative humidity, again, which this is the major driver of how flammable your grasses and your shrubs and stuff are, the Santa Ana winds bring the humidity down to 5 to 15%. In the Rocky Mountains, we have Fein winds. It's similar to the Fein winds in the Alps. I'll show a case for that. The Lahaina fire in Hawaii, the winds there drop down relative humidity to 2%. And the Greek Etesian winds, they drop the relative humidity to 20 and 30, as does the Portugal Ventos winds. And these are winds that are not any worse due to climate change. I think the Etesian winds, Philip of Macedonia, when he was launching his invasions, he used those winds because they blow out of the north and they prevented sailing ships from reaching him as he was doing his dirty work. So these are winds that have been documented for hundreds of years. It's not a climate change issue. So you look at that kind of relative humidity. Well, as we've seen, fire suppression has caused grasses and shrubs to build up and cause more intense fires. We're trying to get rid of some of that, either mechanically by plowing it under, but the most effective is doing prescribed burns. But if you're a land manager, if the fuel moisture gets below 8%, the fire danger is too extreme and they'll cancel a prescribed burn, because a simple spark, an ember that kind of gets away from your fire lines, can just land and start another fire and spread that fire out of control. So they don't like to do it when it's that the fuels are that dry. And it's relative humidity that really guides this. So usually a land manager is referring to some type of chart like this. So you look at relative humidity from 0 to 100%, and you look at how temperature affects it. And you look when relative humidity is 10 to 14%, as it was with the Santa Ana winds in Los Angeles, fuel moisture gets down to 2%. Highly flammable. That's why it was so explosive, and the fires move so quickly from that. Your fire fighters don't have a chance. Your only chance of saving your neighborhood is to have a good defensible space, because you're not going to start a fire with high winds and that relative humidity. What's also interesting, if you look at the temperature, whether it's below freezing or is over 100 degrees, 2%, 10 to 14% relative humidity will cause fuel moisture to drop to 2%. If you go to the places like Greece and Spain and Portugal, where relative humidity dropped below 30%, you see fuel moisture again is 5 to 4%, still way below that 8% mark off. Temperature has a little effect, but not much. So it really, when people say, oh, it's this high temperatures making the vegetation worse and more susceptible to fire, and that's climate crisis, it's bull. It has nothing to do with temperature. You have to look at relative humidity, and that has a lot to do with how moisture is transported from the ocean to the land or blocked by the mountains, etc. In the United States, in the eastern United States, in the summer, when you get more of that moisture coming up from the Gulf of Mexico, you get relative humidity between 70 and 80%. Now you see fuel moisture jumps above that 8% mark. And now it gets 10%, 11% fuel moisture. It's harder to ignite it. It's it's slower to spread, so it's easier to fight. So you don't have that many big fires in the eastern United States like we do in the western United States. But why do the Santa Ana winds have such a low relative humidity? Well, in the eastern part of California and into Nevada, we have deserts. California has like 3 major deserts in the Great Basin in Nevada. The high desert plateaus cool off very quickly in the fall through the winter, much more quickly than the Pacific Ocean can do, because the ocean has a little more heat capacity. And that creates a pressure gradient where you have a high pressure in the desert and low pressure in the Pacific, and that drives these winds down towards the ocean. And as the winds descend, temperature has an effect on relative humidity due to what we call adiabatic heating, meaning it's due to changes in pressure. It has nothing to do with CO2 or solar energy. And we name the Santa Ana winds because it comes down the Santa Ana Canyon, where the winds when they get focused, the winds speed up. And if you ever had a garden hose, and I know I used to have water fights with my friends as a kid, you put your thumb on the end of the hose and you can really squirt far. And that's what these canyons do to this wind. They speed it up. And so this spreads these fires tremendously. So Southern California, these Santa Ana winds happen all the time. Northern California has something similar, only we call them Diablo winds. And people have looked at, well, of how much do these Santa Ana winds cause fire? Well, 75% of the Santa Ana wind events cause no fires whatsoever. What's important is if you have an ignition during a wind event, and that's when you get the big fires. And that's what's happening as populations increase, you're increasing the probability of the two are going to coincide. The other place where you have winds is something a very similar dynamic, but we call them feign winds. And that's because as the winds blow perpendicular to the mountains, the air is forced up. As it cools, it drops its moisture on the windward side. And then as it sinks on the leeward side, the air heats up, but it's dry. So now its relative humidity drops very low. So in places where you have feign winds or a similar type of conditions, these winds are drying out the vegetation in one day, enough to make it these fires very susceptible fires. And I'll give you one example. In Northern California, we had the Tubbs fire in 2017, and these are homes that had been built out in the last decade into the grassland areas north of San Francisco area. And once the fire reaches a congested neighborhood like this, the house radiates so much heat to its neighbor, the whole neighborhood goes down. So when you see here, house after house, they were just too close. Whoever were the urban planners really didn't understand how this was going to happen. The trees don't burn, but every house burns because of the way it's radiated. So if they're going to rebuild in these places, they either got to set up some kind of way to block that radiative heat or spread them out so they're at least 30 meters apart. And what's curious, they should know this because the Tubbs fire that happened in 2017, the wind pattern there going through these canyons in Northern California was very similar to a fire in 1964, which you can see the two outlines, they're almost identical of the way the fire spread due to the way the wind spread it across that type of habitat. And you have in the Greek winds, the Etesian winds. If you see how that comes down on the eastern side of Greece, that's where most of the fires were happening. And if you get, sometimes you get winds blow from the Sahara, which are usually a little drier. In Portugal, you get lots of fires driven by the ventos del este winds, which are coming off the dry, high plateaus of Spain, similar to what we're getting here in California. So it's these dry winds that are driving a lot of these fires. The last point that I hardly ever see any of the media or even alarmists who are writing published papers talking about 1 hour and 10-hour fuels. Because if a dry grass can dry in a matter of hours and become highly flammable, it totally refutes the idea of climate change. You say, well, 1.5 degrees warming since the Little Ice Age in 1850 causes to be a drier situation. When the grass dries out in a couple hours, it makes no sense whatsoever. But that's what they push. If you ever had to start a fire, whether it's in your fireplace or as someone doing a campfire outside, you realize you can't just hold a match to a log. You're not going to get enough heat to do that. To build a fire, you need tinder that's easily lit by a match. Then you have kindling that's a little bigger that's easily lit by the tinder. And then the kindling can create and sustain enough heat that then it can light a log. So you really need these steps to have a forest fire. Well, what your fire managers, they look at this, and what we will call the tinder are 1 hour fuels, dead grasses. And we know that they can dry out in a couple hours. It could stop raining at 7 in the morning, and by noon it's dry, and these fuels are highly flammable. 10-hour fuels, it might take 2 days. And if you have high sun and high winds, it adds to that, making it all dry out a lot quicker. So when you're highly flammable within just an hour or a few days, climate change is irrelevant. So, and if you doubt my word on this, go home and soak a piece of computer paper so it's thoroughly, and then hang it up and see how long it takes it to dry, or cut it into strips and see, every hour, see how quickly, when does it become highly flammable. And you'll see what's key to getting these big fires is these 1 hour and 10-hour fuels. So if we look at how this vegetation works, the Mendocino fire, the third biggest fire in California, was a grass fire, 1 hour fuels. A rancher was pounding a metal stake into the ground. He hit a rock, it caused a spark, and that, even though it was just a split second, that was enough to ignite the grass and cause the third biggest fire, the Mendocino Complex fire in California's recorded history. Now you compare that to a lightning hitting a living tree. The lightning strike is 50,000 degrees Fahrenheit, 5 times hotter than the surface of the sun. Yet it's happening so quickly, it doesn't have enough sustained heat to ignite the tree. But it can vaporize the moisture in the tree and cause a scar like this, or a branch to blow off. And usually when a lightning strike causes a fire, it's because it hits some kind of 1 hour, 10-hour fuels at the base of the tree. To get a tree to burn, you have to have a more sustainable heat than what a lightning strike would have. And that's where this fire suppression came in. When you allow more grasses and shrubs and stuff that are easily ignited to build up, carry the fire into the forest and support it until it can burn trees, that's when you have the real problem with forest fires. But again, the key is these 1 hour and 10-hour fuels. If you have a forest where you don't suppress the fire and it's keeping the vegetation low, it will sweep through without lighting the trees on fire. But when it gets to a place where there's a lot of understory, they create like fire ladders where you're allowing the fire to get in the canopy. That allows more embers to spread it. It can burn the whole tree. It becomes a problem. So if we look at places that had a forest had fire suppression, once that fire gets in, the whole place goes up and you're left with a totally devastated area. Where if you have a place that we've allowed fires to happen, or we've managed them ecologically, a fire will come through, it will just burn the grasses and stuff really quickly and move on before it can ignite the rest of the trees. And now you have a forest with kind of an open parkland field. And a lot of the forests in California, like Ponderosa fires, are like this. And we can see pictures of historical evidence of, with lots of fires, we had these kind of open forests that didn't burn. The trees lived forever, as long as they could. So if you understand it, it's these dead grasses and these 1 hour and 10-hour fuels that cause the most burnt area. If we look globally, we'll see shrublands and grasslands and savannas. And savannas are basically a grassland with a scattered amount of trees, but you're getting up to 200 million hectares. And in terms of acres, that would be about 500 acres or so. The forests have a much smaller area that's burnt, and croplands also and a lot of what they call croplands or croplands have been abandoned and where fuels get to build up. But globally, you see two things. Most of the burnt area happens where you have these 1 hour and 10-hour fuels, and it's not expanding like you would think the way they're pushing the climate crisis. California, we have the same thing. When they started fire suppression, there used to be a lot more, but it was mostly grasses, mostly shrubs, the 1 and 10-hour fuels. Very little in the woodlands. That's decreased, but it's still grasslands that carry the day with the fires. And what's happening more is we've disturbed the soil and done other things. We have more invasive grasses coming in that are expanding the places that can be burnt and how quickly they will be burnt. And one example here is Malibu Canyon outside of the Los Angeles area. Because humans caused 2 fires every 10 years there, where there were never any lightning fires, what used to be a chaparral area with shrubs has been converted to an invasive grassland. And now that invasive grassland is more easily ignited, more rapidly spreads the fire, and creates a danger. If that fire spreads too close to your towns, your firefighters can't stop it. It's just happening too quickly. And you can see part of the West where we have a lot more fires. There's this cheatgrass that's come in from Eurasia. It germinates in December, and at the end of our winter and rainy season, and it's usually dead by April. I see this grass around me now is dying. And so you have from May through October and November, these grasses are highly flammable. And it's this kind of change that what we've done to the landscape is what's making this slight uptick in fires that we're seeing today. In Greece, Portugal, they're suffering from a lot of the same thing. They have a lot of grasslands that are maybe 10%, but if you include pastures and overgrazing and abandoned agriculture, once you abandon the agriculture, what you have is these invasive grasses come in. They're highly flammable, easily ignited, and it only takes them a day or two to become flammable. And so that some of these fires that we're seeing all around the world is like that. Well, the fires that went to Los Angeles, this is the way the habitat looks. Lots of dead grasses, some dead shrubs. We're not sure what started it. It definitely wasn't lightning. But once this was ignited, and people say, oh, it was the drought and climate change. It made it so dry that these things dried out. Well, these are 1 hour and 10-hour fuels. You know, that argument is just malarkey. It's just, they're just trying to push a narrative without looking at the science. It's true that these fires, the rainy season didn't come as quickly as it did, but that's due to La Nina, and I'll mention that in a second. But once the Santa Ana winds picked up some kind of ignition, it just blew it down to the Pacific Palisades. And like other places where all these houses got very congested, you'll see some houses totally escape because they had defensible space, but house after house that was very close to each other, they just ignited. And once you got the flames in there, and you have an ember, if it can get onto your roof, you have a flammable roof, or it can get in through a vent, you can set a whole neighborhood on fire. I don't know if people would remember, there was a Marshall Fire outside the Boulder, Colorado area in 2021. And here you had fane winds coming over the Rocky Mountains in late December. And these fane winds are very dry and high. And they had some communities outside of Boulder that built in to the grasslands. And so as the winds came over, and what we know, it was a faulty electrical wire and some careless debris burning that ignited the fire, and it carried it down to these towns. And again, it wiped out all these towns, house to house. They were too close. They built out without thinking of how these fires were going to affect them. The Lahaina fire in Hawaii, you have the trade winds, and you think the trade winds would be very moist, but normally they are, but going up and over the volcanoes and coming down to Lahaina, which is sort of the red triangle, you have a fane wind effect. And there they measured the relative humidity down to 2%. And if you look at the landscape around Lahaina, above the coast were all these agricultural areas that had been abandoned. So you had these invasive grasses and shrubs that were easily ignited. Once they had a spark, it just carried it into the town, and it was just devastating for the town of Lahaina. We see something similar in Portugal, where it's these 1 hour and 10-hour fuels. You have these natural grasslands combined with abandoned places that just carry the fires into different places. The Greek fires, the majority, they had in 2023, they had about 667 different fires, and they blamed them all on human ignitions. And they actually arrested 24 people for arson and 118 for negligences, for the ones that could prove. But what we saw is the media going, the world is on fire, it's due to climate change as wildfire rips through Greece. And people just don't realize that Greece is a Mediterranean climate that is totally susceptible to this kind of fire history if you don't protect against it. And it seems like they're trying to keep the blame on burning fossil fuels. So they offer the lion's share of funding it. Can you find a way to blame CO2 for droughts, for floods, for wildfires? So we had this paper come out last year from University of California, Riverside, that said CO2 is worsening wildfires by helping plants grow. And I said, I just had to throw my hands in the air. It's like CO2 is the life molecule that allows plants to grow. And now you're trying to say it's causing fires. You try to shade everybody's opinion on something that's totally innocent and totally beneficial and make it look bad so you can have some kind of government regulation. It reminded me of a W.C. Fields quote where you can fool some of the people some of the time, and that's enough to make a decent living. And that's what I feel like these grifters are doing. They're trying to fool you with this stupid crap. But anyways, I don't want to digress.
There's nothing it cannot do.
It's not cold, warm, hot. So, and then another person, Daniel Swain, who's a California weather person. He's a good meteorologist, but he's a climate alarmist, good friends with Michael Mann. He has the Weather West weather blog. And his weather stuff is not bad, but he's been pushing this climate whiplash and saying, well, CO2 and good rains cause all this vegetation to grow. And then a few years later, you have dry conditions, it dies, and now you have worse fires. So trying to blame the same kind of thing. And he's calling it climate whiplash. And when he just put out a paper earlier this 2025, and the media jumped all over it. Everybody's blaming climate whiplash. And they're saying that it was climate whiplash that caused the wildfires in LA. And it's total horseshit. But anyways, it's based on a certain fact. And almost anytime you see a story that says we're having more extreme weather, more drought, more floods, more wildfires, because when you warm the atmosphere by 1 degree, it will contain more water vapor, 7%. And I've seen that in hundreds of different articles, and it's an undisputed fact. It was in the 1800s they were testing this, and so we know that the maximum capacity can be raised by 7% for 1 degree, but you can't apply that everywhere. Daniel Swain, again, to try to make this more palatable to people with a 9th grade education or so, it made the analogy that when you warm the atmosphere, you're making the atmosphere act like a bigger sponge. So a bigger sponge can absorb more water, making more evaporation, causing more dryness. Or if you squeeze that sponge out, then it's causing more moisture to fall and you're causing more flood. So he found a way to kind of blame CO2. You assume that it's CO2 that's doing the warming, and then you're blaming the sponge. But what he's ignoring is the fact that it doesn't matter if you only have a little bit of moisture. It doesn't matter if you have a small sponge or a big sponge. It's what controls a lot of this is moisture transport. But he's pushing this hydroclimate whiplash to say more evaporation causes more droughts because of the bigger sponge, and a bigger sponge causes more precipitation and causing more floods. So what I just want to push right now is there's 2 major natural climate dynamics. There's a few others, it will take too much time. But what causes droughts, floods, and vegetation is the way that the Earth's moisture is transported. And it starts off where it's absorbed from the ocean, but 90% falls back to the ocean. And then 10% gets transported to the land, but it gets transported into the land in different ways, and the mountains can block it, causing one side of the mountains to be lush and the other side to be a desert. So the first major dynamic, and I'm amazed when I ask people, and I've given a number of talks, I ask people how people know the Hadley circulation, or how many people know the intertropical convergence zone. And I barely get 1% of the people that have ever even heard of it. Yet it drives most of the moisture, and it also is the reason we have the Mediterranean climates. And the reason for this is totally solar powered, that the sun's direct rays heat around the equator the hottest, and then they get less and less as you go away towards the poles. And so you create this temperature gradient, which causes a pressure gradient that drives the air towards the equator. And that creates the trade winds. Now, when the trade winds bring this moisture-laden air where they converge, they have no place to go but up. And where they go up, it finally cools and it falls back. So 30% of all the rainfall across the globe happens just beneath this sort of narrow intertropical convergence zone. And it will shift. The other thing that once it's up there, all this air is lost all its moisture. So now you have this dry air. It diverges away, and it eventually, what goes up has to come down. So you have this dry air sinking 20 to 30 degrees latitude north and south of this ITCZ. And that causes tremendously dry areas. It causes deserts. It's all your heat waves are due to this exact same dynamic where you have descending air that's dry, you have fewer clouds, you prevent convection because the air is coming down, and that high pressure is what causes this dryness. So you have areas, they're not dry because of increased evaporation, they're dry because of the lack of moisture that ever gets transported that way. And if you look at the power of this, if like an ecologist is how I got why the Hadley circulation meant anything to me, is that different biological life zones are dependent largely upon the way the circulation works. So if where you have the wet part of the Hadley circulation, the intertropical convergence zone, that's where you get your tropical rainforests, because that's where all the rainfall happens. And those are the green areas here. Where you have the descending dry air, the high pressure systems, that's where the Earth has its deserts. Now, the exact area is modified a little bit from depending on how much moisture can get from other parts of the ocean and the rain shadow effect from mountains. But that's pretty much the reason we have these deserts. And that's seen in kind of the orangey mustard areas like the Sahara. And these areas of the desert, they're not dry because it's hot. They're hot because it's dry. It takes half the energy to heat up dry surface of the land as it does for a wet surface. So if you don't bring any moisture there, you get the hottest temperature. So in Death Valley, California, the record for the world is 134 degrees Fahrenheit measured at 6 feet above the surface. But that happened in 1913. What used to be a record, but there were some irregularities, so people have challenged it, was 136 degrees in the Sahara in Libya in 1922. So it's not like CO2 has caused these to go up any higher. We now use satellites to measure surface temperature, which is always going to be hotter than the 6 feet of air temperature. But satellites over the Lut Desert got 177 degrees Fahrenheit on the ground. So these are hot places because they're dry. Now, even in tropical rainforests, because of the tilt of the Earth's axis, the ITCZ moves north and south. So in the summer, it moves north. So the area underneath the red, all those areas have their rainy season. And the things in more the gold country will have a dry season. And then as the tilt of the Earth changes with the orbit, and now the sun appears to move to the south, now the golden area has its wet season, and the places under the red area have their dry seasons. So you have these wet and dry seasons, and those dry seasons are susceptible to fires. And people who are clearing their land in the tropics, they'll take advantage of this swing of dry season. And the thing is that the tilt in the axis it has a 40,000 year cycle called the obliquity cycle. And it used to be a greater tilt, so the ITCZ moved further north. So between 10 and 7,000 years ago, the Sahara was a moist savanna with lakes and tons of wildlife and hunter-gatherer populations. And then by around 7,000, 6,000 years ago, as the tilt got less and less, the ITCZ didn't move further north, and it turned into a desert. So again, it's this kind of natural cycles of the way this ITCZ and the Hadley circulation affect things cause how dry and how wet it can be. And there was a whole lot of talk about Pakistan flooding, and it was due to CO2. And Pakistan is usually a desert, but it's affected by the ITCZ. And just to mention that, I don't know if anybody has ever heard of a guy named Winston Churchill, but he said, never let a good crisis go to waste. And the UN Secretary Guterres has taken advantage of that and said, well, Pakistan has happened today. Tomorrow it could be you, to kind of push this climate fear. And all the media picked up on that. So Pakistan emits less than 1% of the world's planet warming gases, and now it's drowning. And to make it even worse, they're blaming you, all you racists out there, saying that Pakistan highlights climate racism, as if that has anything to do with this. But if you look at Pakistan's history, and Pakistan has like 4 deserts, I believe, it's very variable because the ITCZ is very variable, like just how far north and east or west that it will affect stuff. And its worst was in the 1870s, it had one of its worst droughts, not due to cold temperatures, not due to the smaller sponge, but the way moisture got transported. And with that lack of precipitation, it caused probably one of the worst droughts and famines that we know of. And this was the 1876, 1878 Great Famine. Northern India, you should be part of Pakistan, also 7 million deaths. Well, what made that so worse? Well, part of it has to do with the El Nino oscillation. And when they had a large El Nino, it caused, and I'll explain why, it caused not only tremendous drought in India and Pakistan, but all around the world by these teleconnections, the way it affects the jet stream. And they estimate between 30 and 50 million people died from this natural variation. Nothing to do with CO2. It was very low then. Nothing to do with warmth. It was very cold then. So the second dynamic that I want to push, and again, there's a few others that I'm ignoring for sake of time. You have this El Nino Southern Oscillation. And the reason we have that is as the trade winds approach the equator, the Coriolis effect causes those winds to curl to the west. And so what that does is it sweeps up all the heated tropical water from the Eastern Pacific and pushes it to the Western Pacific and Indian Ocean. So what you get is this Indian Ocean and Western Pacific warm pool with the warmest ocean temperatures in the world. And that causes all this convection to happen centered more here than any other place. And it causes upwelling of cold water along the coast of the Americas. And that's what we'll call a neutral or a La Nina-like state. So if you say, so here's the bluish areas is when it's colder than average in the Pacific, and the orange areas is where it gets warmer. And whereas the warmest is where you have all this convection supplying all this moisture to Asia, Southeast Asia. And to have a La Nina event, which is a little different, is when that upwelling of cold water becomes a little more extreme, the area within the red rectangle, if it's about a half a degree or more or colder than average, we'll say it's a La Nina event. Now, the other thing that's...
How does the ENSO affect the monsoons? Can you go back?
Here it's supplying all the moisture here. And where this is right now over, say, northern Australia, it can move a little bit further east also. But you're causing this, just like you have an intertropical convergence zone carrying all this moisture to the warmest parts. This part of the Pacific has the warmest parts, which is causing a convergence of moisture-laden air rises, and different circulations will carry it different ways. The other thing is, as the winds push all that water to the west, sea level rise in the Western Pacific gets a 0.5 meter to 1 meter higher than the Eastern Pacific. So gravity is kind of eager to pull that water back towards the Americas. The other thing it does is that heated water is salty and denser, so it can get stored down to 200 meters. So you have this tremendous reservoir of warmth. This is one of the reasons you have an imbalance in incoming sunlight, is because it gets stored in the oceans. Well, if the trade winds are weakened from a burst of westerly winds or a few other things, that causes all that water to rush back towards the Americas. And that's when you have an El Nino-like condition. And what you see is, well, so why did the El Nino cause the tremendous drought in India? Well, what used to be a lot of moisture during a La Nina-like condition, that moisture is now moved towards, that convection is moved towards the Americas. And now you're having dry descending areas over that region. And so now you're getting droughts because of this El Nino event. There was a few other contributing factors, but this was the major one. So in an El Nino event in itself, again, they measure something within this red rectangle. If temperatures go a 0.5 degree above average or higher, then you say it's an El Nino event. But this warmer in the Eastern Pacific, cooler than average in the Western Pacific, it can last 15, 30 years, which has other implications, but it's too much to go into. For us in California, what I had to understand is the El Nino effect has a tremendous amount, that high pressure system that blocks the rain from reaching California in the summer, it can be weakened a little quicker by an El Nino event, making it a little warmer, making these rising convection that weakens the high pressure systems. But when you have a La Nina event, it can increase that. So in California, we had the rains in Los Angeles. They said, oh, it was climate change. We weren't getting any rains in January or October. Well, that's a La Nina event is what you expect. It keeps that higher pressure systems that pushes the water further north. In Northern California, we had as much rain as we could hope for. If not, in some places it was higher than normal. But in Southern California, it was delayed. But again, if you have 1 hour and 10-hour fuels, it doesn't matter if it's delayed for a month. Within 2 days, it's dry and flammable. And just to look, are there any trends? Well, if we look at a standard precipitation index for the Sierra Nevada, which catches most of the rain, again, we see lots of variability, but no trend. And you expect this kind of variability of wet years from El Ninos, dry years from La Ninas. And I know all my ecosystem research, I had to account for that. And you really could see how it affected how much wildlife moved up the Sierra, down the Sierra, whether it was dry, et cetera. It's just what they push this hydroclimate whiplash is really just another name for natural variability. And I take that as a major problem. So just to kind of finish up on how these natural climate dynamics cause fires, you look at the places where you'd expect no fires are kind of white. So you see Greenland, naturally, there's also mostly glaciers. You see the deserts of the Sahara or the Mongolian desert. You don't get fires there, and that's mostly because even though it's warm, you don't have enough vegetation to maintain some kind of fire. In Nevada's desert, the Great Basin Desert, that's just east of the Sierra Nevadas, we're having an increase in desert fires, but that's because that invasive cheatgrass is now allowing it to burn longer. If you look at where the tropical rainforests are, say in the middle of the Amazon or Central Africa, we hardly see any fires there because it's so wet. But what's interesting, between the desert of, say, the Sahara and the African rainforest, that red area is where you have a tremendous amount of fires. In the same way, just south. And that's because the kind of life zones that you have is between very dry and very wet. You have a kind of semi-arid, which creates these grasslands. 1 hour and 10-hour fuels, they're highly susceptible to fires. So if I just run down real quickly, where you have the tundra, and you don't have much vegetation there, you only have 1 to 2.5 million acres that get burned every year, which you'd expect. You have the snow there, it doesn't melt till late, it's a very short season. You go a little further south to the taiga, now you get a few more trees that come in, but you have a lot of shrubs and some grasslands that can carry the fire. So this actually becomes a very fire-prone area, and it's very susceptible to lightning strikes because of the coldness. The debris that builds up here doesn't completely decay. And so we have a lot of a high layer of peat that it can have a lightning strike hit it and it will smolder and it could stay there for weeks until the winds can flame it. So you have a slightly different dynamic happen in the taiga. If you go to temperate rainforests, which most of Western Europe, Eastern United States have, you have a lot of deciduous forest, but enough rainfall, it tends to be moist. You get a lot of rain during the hottest months. And now you get 5 to maybe 12 million acres of fire that gets burnt in that region. But if you go to the tropical savannas, it's seen here in the green, you see how it matches up with the highest burn area globally in Africa. Well, now you're getting over 1 million acres being burnt every year. And again, it says 1 hour and 10-hour fuels that are really the controlling factor. You go to tropical rainforest, and now that drops down to 5 to 10 million. And because it's so wet. And a lot of the fires in these tropical rainforests, especially like Brazil, is where people are trying to clear the land. So it's hard for them to say how much is it a natural fire versus a clearing of the land fire. And it would probably be much less if people weren't there causing the ignitions. We go to temperate grasslands again, we see a tremendous amount of fires due to the grasslands, 31 million acres. And in the deserts, now you're below 250,000. So just do a summer, you can see the deserts have the fewest fires, tundra the next, tropical rainforest the next. And then when you get temperate forests, you get up to 5 to 12, but it's not much different than a rainforest. But once you get to the grasslands, now you're having a tremendous amount. So you're having, in tropical savannas, 750 million acres can get burnt every year. And some of that will change. You can have spikes that go above the average. So when we had an El Nino year, 97, 98, the Indonesia had a spike in fires because it was dry, not because it was greater evaporation, but the normal rainfall moved towards the Americas, and we had floods in California. So the gist of all this, I'm trying to say, climate change has very little effect on wildfires. You have to look at these 1 hour and 10-hour fuels in human ignitions and when that correlates with a wind event. And now I'll try to answer anything you hammer me with.
Excellent as always. Thank you so much. Rather than me commandeering, I'll let anybody. You want to keep the slides up in case you need them, Jim, or do you want to go back?
I could not share, but anytime does anybody want me to share a slide first? I'll do that before.
Anybody have a question? Go ahead.
Yeah, I'll do, Jim.
Hi.
Isn't absolute humidity a better way of measuring the amount of water vapor in the air rather than relative humidity? Because relative humidity is relative to the temperature, and absolute humidity is the amount of water vapor in the air at the time.
You're right that absolute or specific humidity is if you measured how much moisture was there and weighed it, you get a certain amount. And relative humidity, and they also like to talk about vapor pressure deficit fires of what's the maximum capacity at a given temperature. So, but and maybe let me see if I can swing back to that graph I had on Come on, I know you're here.
Yeah, I ask because I measure relative humidity, temperature, thermal dew point, and absolute humidity as part of my everyday work. I do internal environmental assessment, and
Keys for Micah.
Okay.
it's, for me, it's when you start raising the temperature, the relative humidity goes down, but you've still got that amount of water in the air.
Right. And what you're saying is exactly right. But say if I use this and we look at 10 to 15% relative humidity, the fuel moisture was down to 2. Well, the relative humidity is telling you how much you could suck out from evaporation. So how quickly you can cause these fuels to dry out. So, but if you just gave me specific humidity, that wouldn't give me that understanding. But you're right. You're right. If you look at it and say, if at below freezing, relative humidity of 2% means there's very little moisture in the air compared to very little specific humidity. Compared if it was 2% at 109, you could still have a lot more specific humidity, but because the temperature is so much higher, then relative humidity goes down. But it's a relative humidity that causes the evaporation and the dryness of the fuel moisture.
What's the definition of relative humidity?
The capacity of the air to hold moisture at a given temperature. So and the dew point is your 100%. If you want to know how much moisture sometime, and the weather, the weather meteorologists always used to tell me relative humidity and dew points. So you could kind of get an estimate of how the temperature is affecting it.
So Jim, I found that graph to be very informative because I talk with my colleagues, and some of my colleagues have called me up and say, "Oh, I've got 85% relative humidity in this building," and I will say, like, I need the temperature as well, because then you can calculate absolute humidity. So one measurement on its own doesn't really inform me. And to see like the relative humidity, say 10% versus at Fahrenheit 14%, we can get an absolute humidity calculation off of that.
Right, and the key is not temperature, the specific humidity, but how's the vegetation reacting? So in some places, a low relative humidity won't make a difference, like the Sahara or the rainforest. But where you have a lot of 1 hour and 10-hour fuels, those fuels react to relative humidity. Or I don't know, do your colleagues use vapor pressure deficits also? That seems to be a new in vogue way of talking about the same thing, basically.
Not really, but like when I do an assessment, I always take the external conditions, take measurements of what's going on outside. So almost sort of like on a daily, weekly basis, I'm watching the relative humidity, temperature, absolute humidity, and thermal dew point. And over the years, we see that the winters are much drier than the summers in terms of humidity.
Well, we just had the South Carolina fires, and I had people say, how come South Carolina is so humid? I said, well, it's in the summer, but you have, the Clausius-Clapeyron relationship says colder air holds less moisture. And so when you have these cold fronts bringing dry air down from Canada, you cause a drying of the vegetation, and relative humidity in South Carolina in the winter drops to about 30% or lower. And that's when it's like February and March is when the Carolinas have their biggest fire danger, because it's due to cold. And it's because you're having less specific humidity, even though it's colder, bringing it to the terrain there. And if I grew up on the East Coast, so that you have these fire adapted plants. The savanna areas are adapted to fires all the time. So it's you have to look at a combination of all those things.
Absolutely. Yeah, I'm going to finish up with my question now. But I read a book on hop growing, and it's all about beers, and it related to like some of the graphs that you were showing. hops being grown around the world. They only grow in
for beer.
environment. Yeah, I thought that was quite funny. But thank you.
I mean, that's we've brought here in California. I can name 50 different invasive plants that are, some are very beautiful, but they also screw things up. In Portugal, one of the things, they started planting eucalyptus trees after fires. But eucalyptus trees, and we've done that here in California from Australia, eucalyptus are very fire prone. And they've added to their problems by bringing in different plants to different habitats they're similar. It's like California and Australia have some similar dry weather conditions. In Portugal, eucalyptus can hit in all those three places.
I've got a photograph of me standing next to a wildfire in Darwin, or just south of Darwin, a few years, well, 30 odd years ago, and it was just hardly burning, really. Whereas I see the results of a wildfire in South Australia, which was dry, and it just covered the whole horizon. Everything was black.
They have some tremendous bushfires there, and I don't know the history of that of Australia enough, but I've seen a number of the Aborigines. They said that they used to burn on purpose, because often when you burn, you open up an area to a little more diversity if it's a good controlled burn, not a devastating burn. And I think people learned a long time ago that a little bit of fire is a good thing. So fire suppression is a bad thing.
Okay, next we have Nigel.
Hello, Jim. Firstly, thanks very much. That was a fascinating talk. I learned so much this evening. I particularly picked up on that 1 hour, 10 hour fuel issue, which I'd never really put that together, and that's a really powerful argument. But the question I really got, you live in California. Can you give us a bit of the political side of things? I saw, or I read, I'm pretty sure, that a firm called State Farm and Allstate Insurance were pulling out of California, and I think they were saying it was to do with climate change. But was that just a political issue, or can you explain that?
I can't talk to all the mechanics of it, but let me first kind of reference. You had these private companies in the 50s that used to do flood insurance. And the only people that were buying flood insurance were the people who sillily they built their houses on the floodplains, which you knew eventually you're going to get flooded. And the people that lived outside that weren't buying insurance. So you need, for an insurance company to work, it has to pay off your disaster with somebody else not having a disaster. And so the private companies gave up on flood insurance because it just wasn't working. And the government said, okay, well, we feel bad for these people, we'll pay for it. And American flood insurance has run a deficit every year. It makes no sense. And so in a similar way, if you were in a place of high fire danger, and not every place where I live, I have very low fire danger. We have in the summer it's totally foggy, and near the coast, the relative humidity stays very high. What I'm hoping they do is not cancel all the insurance, but if you can create a defensible space, if you have siding on your house that is not flammable, or roofs that are made out of stucco or metal, because you have these embers land on a roof that can ignite your house very easily. So if you can enforce that, but the problem is you have to really enforce it on a whole neighborhood. As I showed you, a whole neighborhood goes down. Just one of those houses has to be bad. One of those houses has to say, okay, I like shingle roofs, and I'm going to put that on in a high fire danger. That roof ignites, and then it ignites every other house, even though that house had other very safe things going on. So I think that's the political dilemma of how, if you can't find a way to charge insurance for the whole neighborhood. And I've done some talks down there and just told people, you're going to have to get your neighborhood groups together survey your area and make a defensible space from ground fires coming up to the houses. So you want almost a gravel, sort of like the warning path in baseball or whatever. You want it down to gravel where the fire can't reach your house, but you also want things to prevent embers. So you want to make sure there's no vents or broken shingles that allow something to get in somebody's house. And that's the problem. So I don't know how an insurance company is going to deal with that, but I could see right now they're saying, well, we're just going to pull out, at least for now, until something can come up that makes it a little bit safer. Does that make sense?
Thank you. Yeah, thank you, Jim.
Corin, did you have a question? You're muted. You're muted. I always mute you because you always have your mic on.
Yeah, okay, I get muted. It's very annoying. Hello. Yeah, so Mr. Steele. Yeah, if I was still in my greeny phase, I'd be saying, yeah, that's all true. Loads of invasive grasses, buildings in crazy places, lots of people, arsons, accidents, and you've got the natural variability to do with how the climate works and the El Niños. That's all true. But surely, if you increase the temperature of the system as a whole, you will get a whole system moving towards a new, hopefully, equilibrium, and there will be more erratic events. That's what I would be saying. Is that true?
I would disagree. If again, what would push is how moisture is being transported.
Yeah.
I can have a higher amount of temperature happening in the Sahara, but that's not going to cause more rainfall. That's not going to cause more evaporation. You've evaporated as much moisture that gets there all the time. How much a higher temperature would have other negative feedbacks? As I mentioned, for the eastern United States, if you increase the flow of moist air coming from the Gulf of Mexico or Gulf of America, depending on what you want to call it, you've decreased the problems with fires. And it's same, and if I look at how hurricanes have switched or tornadoes, I don't see any trends. So even though we have a certain amount of warming, I don't see it causing some kind of tremendous imbalance that's causing more extreme weather.
Okay, so if the infamous Michael Mann were to turn up outside this door now, I would say to him that actually the climate system is pretty much as it was. There's no evidence of these huge changes you're talking about, and it's certainly not 35% more likely that there will be a wildfire in Los Angeles.
Absolutely.
Okay.
I feel like what's the warmer temperature going to go? There's so many ways to look at it. There's 10 times more deaths due to cold related temperatures than heat related. So a little bit of warming is not really going to kill us like people are pushing. A little bit of warming could cause more moisture to come, but it depends, as I was kind of showing you, different places. But say the ITCZ, if we have a little bit of warming, you have a little more clouds, you reflect a little more sun, and it really doesn't change that much. And stuff like the El Nino, there's an oscillation I left out called the Madden-Julian oscillation. It moves across the Pacific. And you have where the hottest starts in the Indian Ocean, you have all this convection, rising air, lots of rainfall, but then that air moves eastward and sinks, causing a high pressure system where it gets hotter. And the ocean gets hotter there. So the lack of clouds makes that water warmer. And where it first started in the Indian Ocean, it gets cooler because of the buildup in clouds. Well, that causes the center of convection to move eastward. And so you can see sort of this negative feedback of when you have more cloud, rising air and sinking air, that's causing where it's hot and dry to shift. And the data that I've seen shows that clouds have been decreasing. And so you could say, well, the sun hasn't changed enough maybe to cause heating. the clouds have dropped a little. That's what's causing a lot of the warming, not the CO2. And there's other issues with CO2. But if Michael Mann shows up at your door, could you punch him for me?
Yeah, I'll give him a bit of a smack, and before I do that, I'll tell him that the clouds are decreasing, and that accounts for a lot of warming, nothing to do with CO2. Then I'll give him a smack.
I
Okay,
appreciate that.
thank you.
I think of fire in the same way as floods and hurricanes, which is that all this stuff is natural. The problem is when humans start building in those areas, right? So
Yes.
so there's really no problem with fire. The problem is humans like to be where fires continually are. And if they haven't seen a fire in the last 20 years, they think, "Oh, this is great. Let's build a house here."
That's what they've done. And that's and I say whoever your urban planners are, they got to get smart on this.
So,
But to
yeah.
cover up their stupidity, they go, "Oh, it's climate change. We couldn't predict this."
Yeah, so this is really policy oriented. It's all policy driven, really. The people who buy and build in these areas have to get someone to, and it's all comes down to money at the end of the day, right?
Oh, I see someone with their hand up. How do you do that
Oh,
virtual?
Liz, go
I
ahead.
never learned that.
Liz.
Yeah. Okay. It was fascinating. Thank you very much, Jim, first of all. But I was interested in the different terrains and the different agricultural practices between California, say, and Portugal and Greece. I live in Greece because in a country like Greece, agriculture is on a very, very small scale, individual scale. We don't get the big estate. And therefore, clearing is really down to the individual owners where that's possible. We don't get big expanses of grasslands as such, maybe where there's been overgrazing on the mountains. And recently there has been an effort there's been a new law last year which required people who had land, say olive groves within 100 meters of a village, to clear the grass at the end of the springtime when it starts drying out. And we've also started getting fire warnings when the relative humidity has been low, rather than just because of temperature. But it's very difficult to see how in a country like Greece you can take very many measures to control the wildfires, because it's the pine forests which become go up in flames, and then the pine cones just jump 100 meters or whatever. It's very, very difficult to stop the fire once it's started.
What's the species of pine there?
There are different species of pine. I don't know.
But when you say they jump, it sounds like it's a fire adapted, because we have a number of pines that are fire adapted.
Might be.
They stay closed on the branches until the heat from a fire causes the seeds to pop open.
Yeah.
And it sounds like you would be in a Mediterranean climate. I would imagine you'd have to.
Maybe, yes. But a lot of the terrain is just inaccessible. I mean, it's ravines, or you can't get to these forest areas. I don't know if that's similar to California.
In some
That's really
places,
my question.
The Dixie fire that we had, which was about 20 miles away from my research station, that was hard to get to. And to make things worse on national forest land, to make it back to nature, they've been closing down their logging roads that used to give people access to these fires, and they couldn't get the access. So it's a mixed bag on that. How big are the fires in individual fire in Greece?
I don't know the areas, but for example, there was a very large fire in the north of the island of Evia a couple of years ago. And they're not huge by, probably by California's
that was
standards.
I guess since you'd have such a long history of small farms, you've created a mosaic of landscapes that prevent fires from spreading very rapidly to a great extent. But I know what I heard, there was a lot of arson in the 2023 fires. Is that what you heard?
There is, in general, there is a lot of arson. I used to teach in environmental science a long time ago, and I remember one of the graphs I presented correlated elections with the amount of area burnt by forest fires, it was a very clear correlation.
Huh.
Because after the legalization of land use tends to change with a new government. So whereas a forested area has to be retained as forest, they can then change the law after an election and legalize the change of land use to building or whatever. I don't know if that's still true. I don't think it's probably quite as clear a correlation, but it does tend to be. There is a lot of arson. There's also a lot of accidental fire because people will burn the olive prunings. They prune their olive trees at this time of year, and then they burn the branches, the small branches. And if the conditions are not, windy or whatever, that can get out of control. Or just glass or something left.
Well, in New England, we had that issue where people would rake all their leaves and they'd have a burn pile, and then it snowed, and they waited as the snow melted, then they tried to light the burn pile. But they had to do a lot of public information campaigns where people thought if the snow just melted, they could burn and would get away with it. But because dead leaves and grasses are 1 hour and 10-hour fuels, that people were causing bigger fires, not realizing how easily it could get out of hand. And that's what you have to either burn it in a container or make sure you have, gravel, dry soil with no vegetation surrounding your debris and no wind. Because if the wind carries an ember outside, it causes a problem. You mentioned it was mostly pines, but I still would say, just theoretically, and you would know more than me, is that you can't light a match and get a pine tree going. You're going to have some of that 1 hour and 10-hour fuels carry the fire there.
Yeah, it's the pine needles underneath the pines.
Needles, okay.
They can't be cleared. And maybe a fire, either arson or an accidental fire which spreads the forest.
And needles are pretty flammable.
Needles are very flammable.
There was maybe 10 hours, 10% of the land was grassland. But some people estimated in Greece it was up to 40% if you counted abandoned agriculture and rangeland and heavily grazed lands in the mountains. I guess you have a lot of, in the mountains, some grazing from sheep and goats or whatever. They're kind of
there is overgrazing.
So
I don't know the details, but we get much more careful instructions now. Like in the beginning of or the end of March, it was hot for a week, and so there was a ban on lighting fires, on agricultural fires for a week. So
that's where people get a little smarter. Okay, we have to.
Yeah, we've had a few catastrophic fires with a lot of casualties, so I suppose they have to be a bit more careful in recent years.
You don't sound like you have a Greek accent.
No, I'm not Greek. My husband's Greek.
There you go.
Okay, I have two questions. Great. I don't want to keep us too long. First is Les, go ahead, please.
Actually, I think
Tony has had his hand up for a long time. I'm sorry.
Do you want to let Tony go first?
Go ahead, Tony. Sorry.
Yeah, I was just going to ask about, notwithstanding humans are actually causing most of the fires, human activity with regard to, say, logging, that's potentially degrading the soil. When you cut huge swathes of paths into forests, you damage the soil, or you allow it to dry out. Is that having more of a detrimental effect with some of these invasive species then coming in, the grasses from that are more likely to dry out? Because I've seen a lot of information on people that promote organic farming, and they say that one of the big bonuses is that if you treat the soil correctly, it really does store a lot of moisture and it is very resilient to drought. So I'm just wondering whether, that inadvertently over the years, the change of practice with regard to land has created a slightly worse or much worse situation with regard to the tendency to dry out and not being protected by vegetation.
Well, I think there's some truth to that. Mostly where I've done my studies, there's been a number of logging. The mycologists are most upset about it because often you kill a lot of the mycorrhizal connections that allow plants to grow better. But I've seen where they've made we call them strip logging, where that opens it up and it's small shrubs. It's just a lot hotter. I have an infrared temperature gun. You measure beneath the forest or beneath where they just cut, and temperature can be 20 degrees warmer on the surface. And how much soil gets replenished by decaying wood depends on how much they've taken out. A lot of times they slash all the branches, and some of that can forestall too many depletions of it. But I imagine after a while it would be a problem. So I think you're right. All those are issues. I just don't know good, strong data on how logging has affected burns, other than what they used to do is have slash burns. All the slash that they cut, they would burn those and they would escape like debris piles. So that's about all I can say.
Les.
Yeah, I'm rather reluctant to ask the question because it's sort of going a bit off topic, Jim. But you mentioned adiabatic heating. You said that as the air comes down off the mountain into higher pressure, you get adiabatic heating, suggesting that's because the air is becoming more compressed.
Right.
Something that's troubled me for a very long time is that it seems logical that the air at the bottom of the atmosphere will be warmer than the air at the top, not just because the warmer Earth is closest to it, but also because it's being compressed by the weight of the atmosphere above it. But yet that doesn't seem to be mainstream thinking. Do you have a thought on that?
Well, I would disagree. I think you talk about lapse rates. That's due to the changes in pressure. So that's been talked about for a long time as a reason for temperature changes. You go higher up, and it's also a problem where if you heat all this air, the air hits the solar heated surface, warms and rises. Nitrogen and oxygen, how does it get rid of that heat? Because it's going to rise, and if it starts to come back down, it's just going to heat up again. So it can never give its heat back to the surface. It has to transfer its heat with collisions with greenhouse gases, and the greenhouse gases can radiate that absorbed heat away. So that's an issue that I don't see them talking about. But the lapse rate is something everybody has talked about in different ways.
Yeah, I agree. Everyone talks about the lapse rate. There's no doubting that. But when we talk about how the temperature of the Earth is 33 degrees warmer with the atmosphere than it would have been without, the whole of that warming is put down to greenhouse gases and not to the compression of the atmosphere by the gravitational force on the atmosphere. Surely at least some of that 33 degrees must come from the gravitational compression.
Well, I would agree. And there would just be a gradient from the surface up to the top of the atmosphere. So,
yeah,
this is Ned Nikolov's argument, but take out the CO2 and the pressure is all the same. So he says CO2 doesn't matter at all. But in fact, as we know from Will Happer, the CO2 effect is tremendous up to the first 50 parts per million, nothing to do with pressure.
Yeah, and that's what I find confusing. A lot of very highly qualified people like Will Happer seem to suggest that gravitational compression of the atmosphere is completely and utterly nothing to do with the temperature.
Well, no, it doesn't, but it just doesn't change. So whatever it is, it doesn't matter.
But you see, the so-called greenhouse gas effect is allegedly proven by that 33-degree increase in temperature compared to having no atmosphere.
This is a total confusion.
Part of that 33 degrees is gravitational compression.
This is a total confusion because water vapor does most of the work. So when there's ice ball Earth, you don't have those 33 degrees. And when there's tropical hothouse Earth, you have more.
Mm. Have you seen a study which looks at the temperature of the atmosphere on, I think it's Mars, where if you go up through the atmosphere, when you come to the level at which the pressure is the same as the pressure at sea level on Earth, then the temperature is the same as our sea level temperature, suggesting that our sea level temperature derives as much from the compression of the gases as anything else.
Let's have another conversation about it. But first of all, Mars has so much less atmosphere than we do. There's no height on Mars. I think you're saying the other way around. The height on Earth is similar to the height on Mars.
Maybe it's Venus. Maybe it's Venus, not Mars.
Venus is a complete disaster, and no one should talk about Venus. Because there are storms on Venus that are like 200 miles tall. It's a completely different environment. And that doesn't relate to anything on Earth. So all of that is just social media hand waving. But Ned Nikolov,
about 215 days,
and I think it's 243 days is one day.
Oh, that's right. That's what I was going to say.
On Venus.
Well,
yeah. So that's just nonsense. But Ned Nikolov is a smart guy who really thinks that the pressure, but I don't see how the pressure changes. Maybe on a billion-year scale, but not on a million-year scale. Pressure doesn't change. But anyway, let's stay with Jim. I'm happy to have that conversation another time. In fact,
what's the compression due to when you have, say, minus 80 degrees on Antarctica in the winter?
Exactly. Well, it's not a lot different. The air pressure, the pressure is about the same. But Les, if you want, I'll invite Ned. I'm not a big fan of Ned's, but I can invite him and he can sit here and tell you, and we can have a conversation about it.
Yeah. Thank you, Jim.
I'm reluctant to invite Ned just because I think he's not worth it, but you never know. Maybe maybe we should.
He's controversial, so
yeah. He's not stupid, for sure. But I've watched enough of his stuff and videos and read enough to think, okay, well, we've got other things to do. Nigel, please.
Yes, Jim. Greg Wrightson shared his slide pack. Is there any way we could persuade you to do the same?
I have a very generous fee structure.
Yeah, Jim is happy to give these talks, Nigel. I would invite him instead.
I will put my slideshow on my Google storage and send the link to it. Anybody with the link can download them.
That'd be brilliant. Thanks very much.
I'll send it to Dave, and we'll just take it from there.
Okay,
I can have that done by tomorrow.
two fire questions for you. First, what if you, Jim Steele, were the director of the fire marshal for entire planet Earth and all forests on Earth, disregarding places where they're just planting so many eucalyptus trees that it's basically a bomb waiting to go off, but just in sort of normal temperate forests, what would your prescription be for burn policy and fuel management in general, without going into specifics? Do you have a kind of a general way to think about it?
Boy, I don't know if I was a marshal, but it depends on different places. Again, I would say that you don't want to have the 1 hour and 10 hour fuels build up. So I could see promoting goats, certain amount of grazing. I think grazing kind of helped minimize some fires earlier in the 1900s. You know, I don't want to just say let it all burn at any time, because you do have to defend. If you've built into the forest or into a grassland, you'd want to defend it. So how much do you defend it? I mean, mostly what I would, you know, just argue, if people build into places that are vulnerable to fires, you got to create a defensible space for your home, for your neighborhood. And that means structurally what kind of materials you use that are fire resistant. You want to keep empty space between the outside, you know, the natural world and your world, so there's not a pathway to your house.
But what would you prescribe for the actual forests? For example, you know, forests tend to catch on fire. Would you put those fires out, or would you let them burn in general?
Well, you know, like ponderosa pines, they need fire. And they want, and the pines do well when it's open and a lot of sunlight. But as soon as the firs come in and invade it, you know, those trees start to die. So there's a certain natural cycle there. But if you go higher in the Sierra Nevada, you get up into the red fir country, and now that's dense forest, and you might not have a fire there, but every 300 years. Where in the ponderosa pine forests that are very dry and at lower elevations, you might have a fire every 10 to 20 years. And some of these grasslands, you would expect fires every 3 to 5 years, just by natural ignitions or whatever. So, and it's hard to know what's natural in the past, because Native Americans did a lot of burning because that opened up diversity for them. So, you know, you'd have to look at each ecosystem and decide what's going to happen, and when is it appropriate to kind of suppress the fire a little bit, and when it's not, based on, you know, what threatens your home. So it's I don't know how I would play God with all that. So
Well, let me ask you a suggestion. Here's a straw man. Let me throw this out. Wherever you are, you look at the amount of fuel in the forest total, you know, underbrush and dead wood and so forth. And when it gets to a danger point, and you know it's just you know, it's ready for a fire, you know that there are winds every year and so forth, then you have to do something. You can't do nothing.
the only thing I would say is, after a fire, I've seen a number of species sprout. They last for a couple of years and then they disappear. And there's been a number of studies that there's certain kind of insect plant relationships that happen only after a fire. On the East Coast, in the Carolinas, you have the longleaf pine, and it's maintained by fire. It has a very special growth pattern that it has to build up its roots, and then it doesn't go very high. It kind of surrounds itself with needles, and then once it has enough energy, then it'll sprout high. And they have like the red-cockaded woodpecker that only likes to nest in those trees, and it's gone. As people have got rid of that and suppressed fires, that tree is lost, and the bird species is lost. So when you say don't do nothing, and sometimes I would say that a fire is necessary to maintain those other species that are adapted to the fire. And so it's just it's not a simple answer, and you really have to go region by region and species by species.
Uh-huh. All right. Well, what would you say in places like the Santa Anas, where the, you know, these Malibu Canyon areas where you know the winds are coming, and so in that case, I guess your answer would be get all of your valuable property and make sure it has clearance.
Yeah, and that's a lot
That's
of
the best thing to do.
a lot of electrical wires, you put them underground, because you get a high wind like that, you cause a spark, and it goes off. There's again, most of those Santa Ana winds, at least 75%, never start a fire. It's only when some human ignition coincides with 25% of the wind condition. So it's, you know, I can't blame the winds. I blame that, you know, we have to develop a culture of being wise about what's causing fires and what drives fires. And
So assuming humans can get enough clearance between their structures or their valuable whatevers and the forest, you're general approach, though, would be let it burn. If it starts to burn, let it burn
In that case, yes.
in most cases, because that's what it's all designed to do.
Yeah, there's just too many species that they're integrated into a fire ecosystem. It's people don't realize how integral it is about with the evolution of so many plants and animals.
So this 10 o'clock rule you would generally disagree with, because if you're out in the wilderness rafting or hiking and stuff, you see these guys with tankers putting out fires all over the place. They're nowhere near a human structure. They're just putting out these giant fires that are just normal.
Yeah, and they're going to a let it burn policy if the fire isn't threatening any structure.
And that's a smart, and that's a generally smart policy.
That I tend to agree with that, yes.
Yeah, because you see a lot of fire putting out, a lot of firefighting in the West.
All over. The Carolinas are always doing prescribed burns, and we're doing it. But I know we've had prescribed burns get out of hand because they
Yeah.
weren't quite smart enough. And
Yeah.
sometimes you just don't know a gust of wind is going to pick up and get you. So,
All right, I'll ask the last question. It's about Patrick Brown. Some of us know his work. He's a fire expert for the IPCC, sort of, and then the fire and the alarmist camp in general. But he's been writing lately about how much of it is rigged and how it's hard to get they don't do very good statistical analysis. But I want to ask you a specific question about his work, and that just concerns strictly the fire ecological, not the data analysis, but his papers on fire. Have you read some of those?
I can't say, but the last thing I read from him was he sort of did a takedown on the hydroclimate whiplash article.
Yeah, not the political ones, but I think that so in his papers he talks about climate change being a major factor in fires.
Okay, I haven't read that. And mostly who I read for California is Keeley. I mean, about 20 different papers from him and several other authors that I don't always agree with, but I'd have to, if you send me a link to that paper.
Well, my question is, are there any good fire science people who are looking at this and saying, just like the tornado, like the hurricane, we had a hurricane expert here a couple weeks ago, and like the flood people, I'm sorry, that attribution stuff is nonsense, and there is no climate change fueled fire.
Well, I agree. I think we've had what's the evolution of the climate attribution group?
But I'm asking, are there fire experts who are writing papers that you agree with or think are skewed? What does the literature look like to you?
It's a mixed bag. A lot of people avoid overarching themes, but some people just give you a good historical look. Sometimes they'll pay lip service to climate science. Say it could be made worse, but we're not sure right now. But Keeley was somebody that I felt was the most objective, and he's written a number of stuff, and it's mostly relegated to the West. And offhand, I'm trying to think who else I would recommend, but at my age, sometimes things don't come as quickly.
So he's not an alarmist, and he's making sense.
No, I mean, he's the one that was saying that saying it's ignitions, not the Santa Ana winds, they're causing these fires. So he kind of looked at it from a very objective point of view.
All right. Okay. Thank you, everybody. Another great experience with Jim Steele. We always appreciate your wisdom, insights, and amazing data and presentations.
Well, thank you for having me. I'm always glad to be here.
We will see each other here a week from today. I think we have we have John Kutch, who is Mr. Lithium. He's a lithium expert, especially lithium policy expert. He's great. So we'll see you everybody next week.
All right.
All right. Thank you, Jim.
Thank you, Jim.
You're welcome.